Right, so today we're going to talk about actually 4 parts of kind of the ML monitoring flow. First, we're going to talk about the problems that we have to deal with after we actually deploy the model to production. And unfortunately, the problems are serious. We're going to cover them in a second. Then we're going to talk about the simplest way to actually address those problems, which is detecting the model degradation with data-driven detection techniques. So we're going to look at what are the potential signals that we can get about the change in the model input distribution. And we're going to also realize that these actually, unfortunately, don't solve the problem. Then we're going to actually look at the ways that we can quantify the impact of data drift on model performance by estimating that impact via some very neat and nifty uncertainty quantification techniques. And then finally, we're going to cover one of the algorithms we invented at NanoML that is also available in our open source package called CBP, which stands for Confidence-Based Performance Estimation. No. This is not easy, guys. OK, let's get started. So first of all, what's the problem? The main problem is that almost all models degrade in time. There is a very cool paper from Nature from 2022 when they basically looked at a number of models across different domains, across different industries, across different model types for all supervised machine learning models. And they look at how strongly those models degrade after you deploy them to production. It turns out that 91% of those models actually significantly degrades after you deploy them to production. If we look at the median here, which is, I think, a nice centrality measure here, we can see that at around 1 year mark, the models on average degrade 20%. So if you're reasonably lucky, you're going to see a drop of 20% off whatever metric you choose, whether it's F1 or root mean squared error or whatever metric you use to evaluate the quality of your model, you're going to see a 20% drop. This is something that's obviously not acceptable to either business or the actual science in us. So if you care about the performance of your models, you need to know what it is. And if we could just measure the performance after the targets arrive, that's it. Our job is done. But this is unfortunately not possible. Why is it? Because the business impact happens before we get access to the target data. Imagine kind of the most typical machine learning use case, a credit loan default prediction. Of course, this will apply to basically any other use case, but I'm just going to be using that as a typical use case that I think everyone in the audience understands. And first, what we get is the model inputs. Then, soon after, milliseconds after, model makes the predictions. Then, based on that, hopefully, the business is actually going to use the model, and it's going to trigger some kind of business actions. Let's say that you decide to not give a loan to somebody, or you decide to actually give a loan, grant a loan. Maybe it's a mortgage. Then, there's going to be some kind of business impact. The bank starts making money because you gave the loan. And after a while, let's say you define your default as non-payment within a year, you're actually going to get the targets. So if your model actually starts to degrade, starts to fail silently right as you make the prediction, because maybe your population changes, then what happens is that this model is going to keep on operating in a suboptimal or failed state for entire year before you actually know what's going on. So to solve that problem, we need to have some kind of early warning signal. And before we start talking about these early warning signals, let's talk briefly about what are the potential causes for drop in model performance. And then we're going to use those to try to find what are the things that we can actually look at right as the model is making the predictions to figure out what are these warning signs for model degradation. First, we have concept drift. Concept drift is simply the change in the relationship between the features and the targets. So exactly what our model is trying to learn when you train a supervised machine learning model. Then we have covariate shift. Covariate shift, kind of on the opposite side of the spectrum, is the change in our joint model input distribution, so joint feature distribution. And just looking at the definitions here, you can already see that for concept drift, we actually need the Ys. We need the targets. So this is not something that we can measure at the inference time. To really measure concept drift and quantify its impact on model performance, we need to get the ground truth. So for the remainder of the presentation, and basically if you look at any drift detection method, library, paper, what you're going to see is mostly focusing on covariate shift, because this is something that we have full access to when we make the prediction. So these are the problems that we have. These are the main causes of the problems. Now let's try to detect these causes. So I'm going to already start with few problems with those. And I'm going to kind of lead with the conclusion here that it unfortunately doesn't work. Why is that? First of all, if you focus on univariate drift detection methods, when you just look at the distribution of two features, one feature, comparing between your test set or your reference data for which you know everything is fine and your current production data, then if you have, let's say, 100 features, 200 features, we even spoke with one of our customers who had more than 1,500 features, then what you're going to get is a lot of false alerts. You're going to get false alerts for two reasons. One is just statistical flux. And secondly, the models, actually, there's should be somewhere here. The models are robust to changes in the distribution. So the model is generally, if you train your model well and the model has good generalization performance, it will keep on operating well even if the data distribution changes. So just because you have statistical significance of your drift, it does not imply performance impact. It does not imply monitoring significance. So this is another problem. And last but definitely not least problem is that if you look at univariate drift methods, you might actually miss some alerts. So you're not only going to get false positives, but you're also going to get false negatives, which actually should be the name of that slide. And the reason for that is sometimes what really matters is the interaction between the features. And as you see here, if you look at the marginalized distribution, they're basically the same. So if you look at univariate drift detection tests, they will not show anything. But if we look at humans from multivariate perspective, then we already see that, of course, this is very different. Basically, what does it lead us to? It leads us to the fact that data drift signals do not correlate with performance. What I mean by performance here, I mean any metric that we want to measure across time or maybe across domains or segments of our population. And what we're going to try to do here is we did a bit of our own internal research when we evaluated all kinds of data drift signals, whether you're looking at univariate drift detection models or multivariate drift detection models, and we tried to predict is this going to work? Probably not. And we tried to predict this time series right here. So what you see here is ROC-AUC, which is basically a model performance metric. And we see that in the test set, the model performance was reasonably stable. The model performs well. And then as we deployed the model to production for the first few months, from the first few tens of hundreds of batches of data, everything is fine. And then at this point here, we see this huge spike downwards, which is probably caused by a data quality issue. Then the model performance recovers, but it does not recover fully. So what we want to actually see is, first of all, we want to see this spike here. We want to be able to detect this strong change because that has business impact by itself, even if it is not permanent. And then we want to detect these persistent changes that in isolations wouldn't be very impactful, but because they persist over time, we also want to find them because otherwise we're literally losing money. So what did we do? We looked at drift detection signals. Like, for example, what you have here is a univariate Jensen-Shannon distance, which is one of the simplest drift detection methods. And again, you can look at our docs. It's everywhere. It's also in SciPy. And we trained a linear regression model on the test set to make sure that there is no data spillage. We didn't look at the training data at all. And we tried to predict model performance based on that signal, on that data drift signal. And the idea here is that if the data distribution changes, then the model performance is likely to go to shit. Turns out this actually doesn't give reliable signals. It's either insanely oversensitive when there is any kind of big change in the model distribution. It just immediately drops to almost 0 or to 0.5 in case of ROC-AUC, or it just doesn't detect anything. And we did it for around 600 data sets, and basically that's what we see. Now, just to contrast, and again, I'm going to be leading with the conclusion here, it actually is possible to estimate model performance. This is our most advanced algorithm that we have an archive paper on. And what you see here is that we can actually, if we look at the uncertainty of the model, we can actually take that into account and we can estimate both that drop and this significant persistent drop in performance. Before I go into describing how it actually works, let me just give you the summary of our kind of internal research here, where we looked at our test set, so we just assume that the performance does not change at all. It's constant over time, which is really just a very naive, very bad benchmark. And then we looked at CBP, which is our open source algorithm, and we have the new algorithm called PAPE, which stands for Probabilistic Adaptive Performance Estimation. We're very creative with our names. And we see that we can actually estimate the ROC-AUC. It's a regression problem. It's 1D regression problem de facto. And we can see that actually in terms of both MAE and RMSE, we do better than the test set. And in the contrast, quite stark contrast actually, if you look at the MAE and RMSE of just using data-driven detection signals, you get so many false positives that it's better to assume that the performance does not change, because otherwise you're just going to be drowned in false positives. Moving on now to, okay, so this doesn't work. What can work? I'm going to start building slowly the intuition of how we can actually estimate model performance without access to the target data immediately as we actually make the predictions. First, a lot of probably of you here and me also a few years ago were fully convinced that if the model is really good and it extracts all the information from the data to actually learn something about the target, then we cannot predict performance. Because if we could, it means that there is some additional information that we can just use to improve the model. Turns out that this very easy intuition is actually false in an interesting way. And this example here serves as a kind of a simple introduction to it, or simple intuition. So what you see here is a 1D regression model. We have feature X, we have target Y. We built bias optimal, absolutely perfect regressor here, which is just a straight line because I generated the data to be just a straight line. So it's as good as it gets. What we also see, though, as humans, and it's going to be quite easy for you to understand, is that the level of noise in that region of model input space is very different than the level of noise in this region in the model input space. And that itself, it implies that even though we cannot use that information to say anything about the target, because it's just more noisy, we can say something about the model performance. If you calculate MAE in the region between, let's say, 0 and 2 here, because of this dispersion in the data, we expect to see higher values. So the model is not that good at predicting the values here as it is here. And to illustrate it further, I computed the rolling mean error here, rolling across the feature X. And what we see that indeed there is a roughly linear relationship, taking into account the noise, of the dispersion of the data, which is just, again, a linear function of X, and the actual rolling mean error. So we can estimate model performance even with without access to the target data if we just know the level of the noise in the model inputs. And this is something we can learn. Now, to generalize that to more dimensions, and also talk about classification setting here, where we can do, for example, a very simple XOR problem. What we see here is basically we have a bit of noise. We train a nonlinear SVM, and then how can we actually have this idea or notion of noise? How can we use it? How can we extract it from the model? Turns out that for regression problems, as I mentioned before, we just need to learn the pattern. For classification models, it's even easier, because what we can use is we can use the predicted probabilities as a measure of uncertainty. How do we do it? Basically, we just turn it into model confidence, which is a very non-scientific term. I don't know if there's a proper scientific term for it. Just for the purposes of the presentation, I'm just going to use confidence, which is just how close the prediction is to 0.5. If the prediction is very close to 0.5, then we can say that the model doesn't know anything. Like the model is very uncertain, it's not confident, and we expect the model, and the model itself kind of expects to make a lot of errors. And if it's close to 1, then of course we expect the model to perform well. And now, just comparison here. So what you see is if we have points that are right in the middle of a class, the model is going to perform very well. It's a very easy task. If we have more data close to the class boundary, then this task becomes harder, and we expect to see a drop in performance. And now that we have this intuition, let's talk about how we can actually take it, form it into an algorithm, and quantify it somehow. So what we're going to do is I'm going to focus right now on binary classification. This also extends in the exact same for multi-class classification and for multi-label classification. And there is another very similar algorithm with the same intuition for regression problems. Now, focusing on the binary classification, we're going to look at each of the data points in our current batch of data or our current day of data, and we're going to fill in this kind of expected confusion matrix based on this model uncertainty. How do we do it? Let's start with the first prediction. It happens to be positive. We already know actually something about the confusion matrix. We know that the prediction is not negative. This is trivial, but it already gives us some information. We also know that it's not a false negative or a true negative. What else do we know? What else do we get out of a classifier? We get the predicted probability. And then, right now, just suspend your disbelief for a second and assume that this is a true predicted probability that this data point will turn out to be 1. And then we can talk about getting to infinite sample size and making sure that this actually follows the frequentist definition of probability. But right now, bear with me, just assume that this is true predicted probability. What we can do then is we can say that for this specific point, we can assign 70% of the probability mass, just probability, to true positive. And if we get enough of data samples, if our batch size is big enough, then this expectation will actually converge with reality. So if we have enough points here, we can say that we get the true expected confusion matrix. We keep on doing that for the second prediction. It's negative. The predicted probability is 0.4. We're going to fill it in. And we're just going to keep on adding those points to the confusion matrix. And then we can use that for anything. Let's say accuracy, simplest possible metric. We're just going to apply our normal definition of the metric to that confusion matrix. And we're going to get our expected confusion matrix. There is a few tricks here and there. So I'm simplifying here a bit. But this is roughly what you can do if you have your sample size above 500 data points per batch. But there is an issue. This value here, the y pred proba, is just a number between 0 and 1 that hopefully is kind of rank ordered. So higher values mean that the model is closer to 1. But it doesn't represent probability at all. What can we do with that? We can do calibration. It's a very standard measure or standard algorithm. So I'm not going to go into too much in depth here. I'm just going to give a brief overview that if you train your model, anything that's not logistic regression, so deep neural networks, gradient boosting, random forest, anything else, what you're going to get is that these numbers between 0 and 1 don't actually represent probability. What do I mean by that? Basically, for it to represent probability, we want to look at the bin data. So we want to bin the data between 0 and 1. Then we want to look at the mean predicted probability in each of those bins. And then we want to see on our test set data, so unseen by the model, we want to see what is the fraction of actual positives that we see in the test set. And if this probability is a real probability, then we're going to get an exact match here. We're going to get a straight line. We don't. So what do we do with that? We calibrate. What is calibration? Basically, we're going to fit a 1D regression model here. It can be isotonic regression. It can be gradient boosting. It can be anything. And we're going to straighten that line. That's it. As simple as that. And then, that's exactly how it happens. And then we can actually say that these predicted probabilities, calibrated predicted probabilities, will be slightly different for each point, actually represent the frequentist definition of probability. So we actually know that in expectation for a sufficiently large data sample, we get true expected performance of the model for any metric we want, which is quite cool. There's a few caveats. First of all, it only works if we look at the entire reference set at once, so the entire test set. And it only works for the current reference covariate shift distribution, so covariate distribution. That also means that we cannot directly use it to actually estimate model performance under covariate shift because we are assuming that there's no covariate shift here. Turns out this assumption can be violated, and the actual algorithm still works quite well. And we also figured out a way to make sure that this assumption is not violated, and we can actually calibrate for any covariate shift distribution. But that will be another talk. So now, just to quickly wrap up, you can see here an example of multivariate detection using PCA reconstruction error, which is a quite robust technique for detecting changes in your model input distribution. And you see that it provides no errors. There is no significant change. But we still see a very strong dip in our model accuracy that is captured by CBPE. And we also provide very nice confidence bands. And we see that actual model performance follows that curve surprisingly nice. This is real Kaggle data set. I don't really remember which one. But it actually works on real data, which we're actually quite surprised about the first time we saw it. So that's it. Now to summarize. First of all, model performance deteriorates with time. Almost all models deteriorate with time. They deteriorate significantly, and you get 20% less performance after 1 year. And we cannot just measure that performance because the targets basically never arrive before the damage is done. That also means we need to solve it somehow. But data drift signals, whether univariate or multivariate, actually cannot be used as proxy for model performance degradation because they don't predict model performance degradation. There's too many false positives. The data can actually move to a region that's as certain, the model is as certain about, as performant about, and even though you have drift, it's not going to actually impact model performance. Lastly, we can quantify the impact of that covariate shift on model performance without access to targets. For classification tasks, we use CBP and PAPE, our new algorithm. And for regression tasks, we can use DLE. So thank you very much. And now let's do the questions.